Okay, cool. So thanks for the introduction. So today I'm going to be introducing you to my work looking at monitoring masonry arch bridge conditions, particularly focusing on the effect of the mortar joints in the visual identification of defects. So currently masonry arch bridges are predominantly assessed manually through visual inspection. This needs an inspection engineer to go to site, where on the left is shown a general inspection where he'll be assessing the bridge from ground level. So it's very superficial, and that's done approximately every 2 years. On the right shows more detailed principal investigations, which are carried out every 6 years, and these are carried out from within touching distance of the structure. So these investigations have been studied, and they've been found by several different studies to be quite questionable in terms of their reliability. One such study is demonstrated here, where they've compared the effect of close-up inspection, general inspection from ground level, and also using LiDAR data and digital data to identify the different proportion of defects that were identified in the structure. As can be seen at the top, on the stripy ones are the manual inspections. At the top, the proportion of defects which are getting identified are getting lower, and that's because it's conducted from ground level, so it's not really being able to see from up there. Additionally, for the close-up inspections, there was found to be a big discrepancy between the two inspectors who were doing it. So both inspectors carried out the same inspection, and only a low proportion of the total number of defects in the asset were actually identified. So therefore, there's potential to improve on this existing process to improve on the reliability of the data. Okay, so what's been done currently to address this? So on the right of this slide is different vehicle-mounted sensor platforms which are currently existing. These sensor platforms are able to take both geometry data and image data, and they can produce a pretty nice 3D model of the structure. However, that 3D model isn't really that much use because it still will have to be trawled through by an inspection engineer to be able to tell where the defects are in that structure. So one project which has looked to address this is this project called Defect, which stands for Digital Image for Condition Asset Monitoring. That was a project conducted by Network Rail in collaboration with some other partners, and that is looking, it's detailed, the basic premise of that is detailed on the left of this slide. It's looking to detect changes between two readings of a structure over time. This was primarily used for tunnel infrastructure, which is much easier to locate or to match together two independent readings because it's a nice long piece of infrastructure. Whereas I'm looking at masonry bridges, which are smaller, and therefore to match together these two pieces of these two readings of the infrastructure, to take change detection, it would be a lot harder. So therefore I'm looking to detect these defects using a different process. So to summarize so far, we've got the drivers for looking to automate this detection, and that is the need for a man to go to site in a potentially dangerous position to assess the infrastructure, and also the subjectivity of that assessment he's giving in the first place, and then also the enablers of automated defect detection. These are in the form of the fact we can make these really nice 3D models quite easily with these vehicle-mounted sensor platforms, and the increasingly powerful GPU computers, meaning you can process that data a lot more easily. So the first step of automating the defect detection of a masonry arch bridge is to work out what the different things we see on the bridge actually mean in terms of the problem with that bridge. So that is what this work here is explaining. So this is work I've done which goes through the different training manuals for bridge inspectors and the building code for bridge inspectors to work out in a kind of medical analogy from what's observed to what the actual disease behind that bridge is, and then what you can do to cure that disease or what you can do to treat the symptoms, which are summarized in the 4 different columns of this diagram. So the symptoms can be generally summed up into geometric symptoms, which are deformations in the shape of the structure, and also visual symptoms, which are, say, cracks or spalling on the surface of the structure. These symptoms then, by combining, if you find on your detection of the structure, you have several different symptoms altogether, combining that together in a map, going through the matrix, you can then work out what's causing that, and that could be an automated procedure. And then it could, as an automated procedure, give you a recommendation of your cures or potential alleviations for that infrastructure. So the 5 main symptoms, which are identified in the previous diagram, are shown up here. In green shows the visual symptoms, in red shows the geometric symptoms. And as can be seen, the majority of the symptoms in the structure which we're looking at for detecting a problem are the visual ones. And that is the highlight, the focus of this work is looking at the visual deformations. The geometric distortions aren't going to be looked at in this work. So this summarizes the workflow that we're working on in order to get from a structure to getting a geometric and visual model of the structure using these vehicle-mounted sensors which are already existing. And then the work we're focusing on is the green bit of this, which is going from the image data, working out where the defects are in those images, and then working out what the result of having those defects are in terms of the structural implication. So I thought I'd put this slide up because, well, a lot of work has been done looking at image-based defects in concrete infrastructure. And as can be seen on the left of the screen, concrete infrastructure is a lot cleaner than masonry infrastructure in general. So in masonry we have the mortar joints, and the bricks aren't always of a homogeneous color, so there's a lot less homogeneity in masonry infrastructure than in concrete. And therefore the focus of this presentation and this work I'm just presenting now is to look at the result of having that unhomogeneity in the image in terms of detecting defects. So one tool which helps us in this, and this is the classification tool we're using to detect these defects in images, is convolutional neural networks. These have the advantage that you have, so every single layer of this diagram is showing a different convolutional filter. So one example convolutional filter which can be applied across an image is an edge detection filter, and that would highlight edges in an image, whereas using a convolutional neural network, each layer of the network, there can be many different filters which each highlight a different feature of the image, and therefore it can focus on different features of interest. Then on the columns of this, as you go deeper into the network, these features become increasingly more complex. You can pick up increasingly more abstract features of an image. So say at this level, the very top of the network, you might be picking up the edges of the windscreen of the car. Then down at the deeper level, you'll be picking up, say, the whole headlight. And through doing it through this process, it means that potentially the network will be able to look over what the mortar joints and other noise in the images are, because it's looking for a particular feature in the image which it can gloss over all the unhomogeneity in the images. So the particular neural network I'm using is the Inception network by Google, and this is a very deep network. So example here is that box is about the same size as the previous screen I showed, so this has a lot of potential filters that can be applied to the network. So for this project, I've collected data from a series of masonry viaducts all around Cambridge, and these viaducts all show different in brick conditions, different brick colors, different brick situations. And therefore, it means that the data set I've generated is much more general, so it can be applied much more generally to different images of bricks. So in order to create the data set, I've had to manually annotate these images with the different patterns which I want are interested in, so the different defect classes, and also where the mortar joints are, so that I can assess the effect of those mortar joints. Then using a sliding window approach, each of these flashing boxes depicts what would be a window which is taken out of the brick, and then each of these windows are then assigned a class based on whether the map detailed in the previous slide contained or didn't contain a defect. So yeah, and that is used for both training and the testing to test against the ground truth data. So then from that, you get these images of the different defect classes are sliding across the image. So for this work, I've combined all the defect ones, which are all the cracking, mortar loss, vegetation, into one class of defect and versus clean, which is the top right here. So it's just looking at segmenting out the defect regions versus the clean regions rather than actually detecting all these different categories. So in order to investigate the effect of mortar and bricks in the images, I've followed these 3 different classification strategies. The first strategy is not to have any separation between the mortar and brick regions. So therefore, on testing, I would just have one clean class and one defect class, and I'll be tested across the whole image. The second strategy, in orange here, is to test mortar and brick as separate categories. So I'd be having a class of mortar defect, mortar clean, brick defect, and brick clean. And then the third strategy, in blue, is to test the mortar regions and the brick regions completely separately. So that would be, testing on one neural network, brick clean and brick mortar, and then having a completely separate classifier for the mortar regions, and then combining the two together at the end. So the results are shown here for the detection on this image here, which is quite a clean image on masonry, so it's quite an easy one for it. And here is the ground truth data, so it's showing that there's a crack going up here, and then a few other spots of defects around there. Here is the first strategy of no mortar and brick separation. Here is the second of the overriding classification within the classes, and here's the third of processing the brick and mortar completely separately. And it can be seen that on all 3 of these, it's done quite a good job of detecting the defect. Although potentially there is slightly more noise in the no mortar brick separation one, but it's not that noticeable, any extra noise. So all 3 strategies have done quite a good job, really. Then in terms of the performance of these 3 strategies, it's plotted on here. So the F1 score is the harmonic mean of the precision and recall, which are measures of how the proportion of the images which have been detected correctly. And that's shown on the left graph here, and can be seen that strategy B and C are very similar in their results, and they're both slightly better performance than strategy A, which is the no mortar brick separation, suggesting you do get slightly better performance through that strategy. The Brewer score is potentially a better measure of performance. It's a proper scoring rule, and that measures the absolute difference between the predicted class and the actual results. So it's measuring how strong the prediction is and the difference between that. And it's the same result for that. For both of these two, it's also worth noting that the standard deviation of the curve is narrower for strategy B and C, where the mortar and brick have been separated. And that is because where there's more noisy image data, they perform better. And that's what's led to the higher mean. So it's more robust to the noisy image data. So my final slide is looking at class activation maps. This is a process where it's looking at what region of each image placed in the neural network is causing that particular classification. All these class activation maps are for the defect category. So the red regions are showing why the regions of each image that the network is thinking is causing it to be most likely to have a defect. And shown on the top here are examples where it's kind of got a bit confused, thinking that a mortar joint is potentially a defect, and on the bottom are examples where it hasn't got confused, so it's worked out, but that's actually nothing to worry about, so it's completely glossed over the fact there was a mortar joint there. So that kind of says that in some situations maybe it will get confused, but other situations it can work it out. So in conclusion, the current inspection regime on masonry arch bridges has a lot to be improved upon. It's potentially quite subjective based on the examiner's experience, and therefore it's advisable to pursue looking at an automated measure. The disease matrix workflow that was displayed is the first step towards having an automated defect detection system, whereby we can go from symptoms to cures and alleviations for what was wrong with that bridge. And then in terms of the effect of the mortar joints, it's suggested that the prior segmentation of brick and mortar does lead to better accuracy and classification of defects, especially in the case of noisy images, where it's got a much bigger potential to throw off the classification. And that's also shown in the class activation mapping. So thank you for listening, and I'll welcome any questions.